then this comes over here.
Okay, so play would work, maybe. Oh,
And then
no.
we try this.
Oh,
There we go.
what did you do?
X is a hotkey.
X.
And
Just
that'll let you reverse it if you're
Standing up or what? Okay. Like that? Thank you.
Thank you. Wow, it's still pouring in. I'll start as soon as it feels like there's a lull there, but I want to...
No, this is fantastic. I thought it would be like a ghost town this Sunday.
Yeah, it's. I think it's a smaller room than we've had it before as well. I feel like at least a smaller room than we had it last year at LA.
I don't know. And then there's the people watching the painting.
Yeah, which is pretty awesome. I'm really, really cool about that. It's awesome.
Yeah. Hopefully, a lot of the ones that aren't live streaming will be available after. You don't need to do like all external bio.
No, I'm going to do a short bio. I think I've already marked down things I'm cutting out.
Yeah, you can get it from the website. Any details?
Yeah, exactly. Wow.
I'll be all like, I mentioned that thing I did in 1998.
Yeah, I saw all these markings, everyone's bios, but I'm just cutting bits out. They're doing the most relevant
Yeah,
bits.
I realized I actually qualified for the Serigraph Pioneers this year, so I registered.
That's not. I don't know. I like that name. Hello, everyone, and welcome to the SIGGRAPH Physically Based Shading course 2016. This is the 6th edition of the course, I think, in its various lineups, and once again, it's so great to see so many of you here. And once again, we have a really, really great lineup for you. First of all, we have the course webpage you can head to here, find out some more information about the course and the schedule. But I'll quickly just display it up here now. We're starting on recent advances in physically based shading, moving on to unified shading asset development at Lucasfilm and ILM, for looking at physically based sky, atmosphere, and cloud rendering in Frostbite. Then we'll take a 15-minute break. We'll be back with an artist-friendly workflow of panoramic HDRI and physically based hair shading in Unreal. Then practical real-time strategies for accurate indirect inclusion, and then towards bidirectional path tracing at Pixar. So as you know, it's a pretty awesome lineup once again. So our first speaker is, actually before I start with that, we're being live streamed this year, which is really awesome. So not all talks are being live streamed, but I think 50% are, and they're all going to be available afterwards on SIGGRAPH University on YouTube as well. So you have friends watching at home. I mean, you can text them now and tell them to tune in, because it's pretty good, obviously. You don't want to miss out. So our first speaker today is Nati Hoffman. Nati is a principal engineer and architect in the Lucasfilm Advanced Development Group. Previously, he was vice president of technology at 2K, and before that, he worked at Activision as in the graphics R&D for various titles, including Call of Duty. Usually, Natty has done a background in physically based shading at these courses. What we've done this year is something a little bit different. Natty's talk from last year's course is actually online on YouTube, which you can watch, which is a fantastic introduction to physically based shading if you do find you want to freshen up on any of the concepts mentioned today. But now Natalie's talking about recent advances in physically based shading.
Thanks, Steve. And hi, thanks for coming on Sunday. So as Steve mentioned, my intro is a little bit different this year. I'm covering recent work in the field instead of physics and math fundamentals. And first I want to set expectations regarding scope. This course, on its sixth iteration, covers all topics related to physically based shading, from material authoring tools to volume appearance models. Due to time limitations, my survey is going to be a somewhat smaller scope than that. I'll be talking specifically about advances in shading models, and specifically surface shading models, not volumes, even more specifically BRDFs, not like BTDFs, and reasonably general ones, so not like hair, like we're going to hear about later today, or car paint. So this is going to be kind of your mainstream shader that you can use for large classes of objects. And even so, despite the amount of scope, there's going to be more than enough stuff to cover. So before we go into the future and look at the latest research in the field, let's first take stock of what models are used in the present in practice in film and game production. So, of course, all these models have separate terms for specular and diffuse. And the specular term nowadays is pretty much universally based on microfacet lobes. Games typically use one. There are a few exceptions. Film shaders often have multiple. And for NDF, the most common one is probably GGX or Trowbridge Wrights, or also called GTR2 sometimes. There are models that use Beckman. There are shaders that let the artist choose one or the other. And here we're showing an anisotropic version. You notice there's two different roughness values. Games tend to rely mainly on isotropic lobes, and anisotropy tends to be reserved for kind of the rare, special, expensive stuff. And in movies, anisotropy tends to be more of a mainstream thing. And as far as the shattering masking term, current best practice is height-correlated form of Smith, which is more accurate than the uncorrelated form and really not any more expensive, so there's no reason not to use it. And the Schlick approximation of Fresnel used to be pretty much universal, but, and it's still quite common, but we're definitely seeing some alternatives out there. First of all, even though it's reasonably accurate, you can see Schlick is basically the dotted lines, and the real Fresnel is the solid lines, and you can see for most materials it's pretty spot on. For a few, there's definitely some divergences going on there. You can see with aluminum and iron at glancing angles, definitely it's a bit off. And some film shaders have been using RGB valued NK complex index refraction values, which, by the way, from a physical standpoint, have an RGB valued N and K is a bit nonsensical, but I won't get into that now. More importantly, it's not the most intuitive thing for an artist. And about 2 years ago, there's this very nice paper by Gulbrandsen from Framestore, where he presented a more intuitive parameterization for putting a little bit of a corrective factor to get more of that color shift on edges. And there's a few different production shaders, I believe, using that. And the diffuse BRDF that Brent Burley presented last year is a good example of a state-of-the-art diffuse model with various features. And most film shaders use something that's not too far off. Quite a few games do, but you can still find games using Lambert, even nowadays. And overall, the current state of the art isn't too bad. People are making some really nice-looking movies and games with these models. But the status quo has some issues and some limitations, and I think we can definitely do better. Two of these have to do with the available NDFs, that one Lego piece there. And the NDFs used today are all smooth. They're like the one on the left. And that's a good representation of very fine-grained microgeometry. If every pixel is covering tens of thousands of surface details, and they'll average into this smooth aggregate. But many surfaces have much coarser-grained microstructure. You might have a surface where a pixel covers a few dozen elements. And in that case, the NDF looks more like the one on the right, and it gives the surface this complex sort of glinty appearance that currently used production models can't really reproduce. Another issue has to do with shape control. GGX is popular due to its relatively broad tail, but many materials have even broader tails than that. It would be great to be able to control that. And Brent Burley realized that back in 2012, and he introduced generalized Trowbridge Wrights, where you can make the tail as long as you want it. And after 4 years, we're really not seeing a lot of use of that around. And why is that? I believe at least part of the reason has to do with a property called shape invariance. And Eric Heitz showed in his excellent 2014 paper that an isotropic NDF is shape invariant if it has the form shown here. So if you can write as a function of tan to the m over the roughness parameter alpha, divided by alpha squared times cosine theta m to the fourth. And GGX and Beckman, if you look at them, they actually do have this form, and they have this property. Generalized Trowbridge-Wrights doesn't. And why does that matter? If you look at the NDF, you can look at the NDF in a different form, not as D, a distribution of 3D vectors, but as P22, which is a distribution of two-dimensional slopes. And if you look at the NDF in that way, you can see that for a distribution with a shape-invariant form, linearly scaling the roughness alpha causes the distribution in slope space to stretch linearly. Stretching the distribution of slopes is equivalent to stretching the microgeometry. So we can see that for shape-invariant NDFs, scaling the roughness parameter is equivalent to stretching the microgeometry by the reciprocal amount. This property has many benefits. It makes it much easier to extend the NDF to an isotropic form, to derive the Smith shattering masking function, to perform importance sampling, either importance sampling based on NDF or even better, importance sampling based on distribution of visible normals, which is an effective technique to reduce variance introduced recently by Hates and Dion. And we want an NDF, ideally, that, like GTR, it has some parameter like gamma to change its shape. But unlike GTR, for every given value of gamma, we want it to be shape invariant with respect to its roughness parameter, alpha. And there's really no NDF like that in current production use. The other two issues I'll discuss aren't problems with NDF or some other part of the microfacet BRDF. They're basic limitations of microfacet theory itself. Now, microfacet theory, I love it. It served us very well. It's a nice and elegant tool. It derives BRDF math directly from surface physical properties. It's exact, but this very elegance comes from some oversimplified assumptions. And these assumptions can limit the realism and accuracy of our shading models. One of these is related to the usage of the G function. The G function determines what percentage of otherwise contributing microfacets are occluded from lighter view direction, which is fine if you then add in the light that those occluded facets contribute via multiple surface bounds. But of course, microfacet models, as we know, don't account for that. That light is gone, the energy is lost, and things get a bit too dark. And sometimes people use these non-physical correction factors, like the Disney model's sheen term, but it would be nice to have a more principled way to handle that. An even more fundamental limitation of microfacet theory is that it's strictly based on ray optics or geometric optics, and not the more accurate or fundamental wave or physical optics. Now, for many years, the rendering community mostly assumed that this doesn't matter, but there's some recent work indicating that it does, and there'll be more on this topic in a little bit. Now, okay, that was it for the state of the art and some of the issues. Now we're going to look at some new stuff. So first up, some work on data-driven microfacet models. This paper uses an interesting model for fitting purposes. It can be seen as a middle ground between a fully tabulated 4D model and a fully analytic model. It has the familiar microfacet structure, but D and F are these 1D tables extracted from measured BRDF data instead of analytic functions. Now, G is computed as the Smith function based on D, so it's not its own free parameter. The NDF is extracted in slope space, which makes it shape invariant by construction, which is, as we've seen, a good thing. And that lets you vary the roughness and isotropy so you can measure a material and then vary it and edit it. The authors also tried fitting analytic NDFs, and they got good results with GGX in many cases, for Merle at least, not for all materials, but most of them. So to what extent do the measurements in this paper match the predictions of microfacet theory? Because they're basically taking a measurement and kind of shoehorning it in. So if we see anything poke out, that might be a good sign that microfacet theory is incorrect in some way. Now, we know the dielectrics won't match well because this paper, for some reason, didn't try to extract the diffuse lobe, and most of the Merle database are dielectrics. But if you look at the metals, you can look at the Fresnel and see if something there is off. And the Fresnel ramps that were extracted definitely do seem different than theory. Right? Theory tells us it should go to 1, and instead it's going to 0. And if you compare it to a similar analysis that Brent Burley did back in the 2012 course, he showed they're mostly going up, not all of them to 1, and some of them are dipping down, so probably a bit more investigation is needed to understand if these are the same materials. This is another paper. It covers some similar ground, but it has some important differences. It, instead of using kind of an extraction approach, it uses more of an optimization or fitting approach. It's restricted to isotropic BRDFs. It does extract or fit Lambert term. And their model is a lot less constrained by the theory. They're like, okay, we can have a separate red, green, and blue D, and a separate red, green, and blue G, which doesn't really have meaning in the context of microfacet theory. And they have some extra specular coefficient, doesn't fit the model. And they did try to derive G from D, like the previous paper, but they also tried leaving it a free thing and extracting it by itself. And it's worth asking the same question as we did for the last one. The authors claim that the independent G did much better than Smith G, which, if true, might be an interesting sign that Smith G wasn't as accurate as we think it is. But Personally, I've looked through the data. I don't see a difference as striking as that, but I haven't spent that much time on it, so it might be something to look a bit more into. Another potential contradiction would be if G and D, things that their RG and V are supposed to be close to each other, were indeed diverging. And from what I could see, they didn't diverge too much, except for a few cases where you would expect them to diverge, like cloth, where you could have fabric with threads going in different directions that are also different colors, so it's kind of coupled, or metallic paint. Some more recent research, in this case now not data-driven, but analytic microfacet models. This paper took an interesting approach. We want to find analytic models that fit measured materials. They use genetic programming. It actually is a really interesting paper to read, how you can see like Fong mutate into Blin-Fong and stuff like that. And one of the models from there will actually be repurposed into something I'm talking about a bit later. Now, before I mentioned that if we had an NDF that gave you both shape control and shape invariance, that would be nice. And while doing research for this talk, I actually ran into two that, at least on their face of it, it seems like they might fit the bill. I haven't really had a chance to look much deeper into them, but they seem interesting enough to throw out there and see if anyone is interested. So this is a generalized Beckman. It's based on one of the results from the GenBRDF paper I mentioned, and it's actually a secondary contribution in an upcoming white paper that I'll talk about more later, so I won't talk about it right now. Let's focus on the NDF. It does have a shape parameter. It does have a roughness parameter. It is a generalization of Beckman. When gamma is equal to 1, then it basically is Beckman. It is shape invariant with respect to alpha. And gamma controls what you could call the kurtosis of the distribution, right? You give it a smaller value, you get the spikier peak and a longer tail, even lumpy tail in some cases. Another interesting distribution, hyper-Cauchy, originated in a 2006 paper, but it came to my attention in a more recent paper by Butler, who proposed using it to fit measured BRDFs. And it has some of the same good properties as Beckman, the generalized Beckman, I mean. And it looks like he was onto something when he was talking about using it for fitting. So this is an attempt to numerically fit Beckman to measure the measured nickel from Merle. And you can see it's not a very good fit, right? The dashed lines are these nice smooth Gaussian lumps are Beckman, and then you have these spiky things that are the actual measured data. And then this is the hyper-Cauchy fit, and you can see it's a much better fit. So it definitely looks like it's worth looking at. And another interesting fact about hyper-Cauchy, if you set gamma to 2, it becomes not exactly GGX, but at least looking at the math on the paper, having compared the curves, almost. So this maybe could be kind of a better generalized Trowbridge-Wrights in a sense. Next part of the talk, I'll cover microflake theory, multiple surface scattering. Microflakes were first introduced in 2010. The idea is that you want to model a volume that has an isotropic structure, like a fibrous structure or something like that, that isn't invariant to rotation, which is different than having a volume that has anisotropic phase functions in it. And they're an extension of the concept of scattering particles. They just kind of add a bit more structure, a bit more anisotropy. And people were using them mostly for cloth. And in 2015, Hayes et al. Introduced the SGGX microflake distribution, which is basically GGX, kind of two GGXs back to back. And it turns out that SGGX had many mathematical advantages over the microflake distributions people were using before, and you can linearly interpolate it and do good importance sampling with it. So it definitely kicked off the sort of microflake usage. And switching gears for a moment, I talked before about the problem of not having multiple surface scattering. And I mentioned there are some kind of hacky terms, but there are some slightly more founded correction terms in literature. There's one older one from the 2001 paper by Kellerman and Zermay-Kalos. And the lower one on the page is the multiple scattering term for metals from the SIGGRAPH 2014 paper on layered materials, which is worth looking at. They also have a term for dielectrics. But there was, in fact, there is going to be presented at this conference a paper that has a more sort of physically founded treatment of multiple scattering, and it's a rather ingenious way to tie together microflakes and multiple surface scattering. Basically, the authors model a surface as a special kind of volume, and they use some formalisms and some techniques that are normally used in participating media rendering in order to achieve this multiple scattering on a surface. And they prove in the paper that it's mathematically the same thing. Unfortunately, it's a stochastic model. You can't really use it in a real-time shader, at least not for most real-time applications. But the nice thing about this paper is it gets to show us what does it look like when you do it right and what we have been missing. And definitely you can notice it, right? You can see that all the areas where on the top it's without and on the bottom row is with, and then the bottom two, you have a single alone and single plus multiple. You can kind of see all those areas that used to get dark, and really they shouldn't. Now they get oversaturated, which is what you would expect, right? You have multiple bounces, gold on gold. That color gets multiplied on itself and gets richer. Now this paper did a simpler derivation of surface multiscattering, also based on microflakes, and they kind of talk about the topic in a larger sense, and there's some very interesting kind of next steps there. Now, the ability to model sort of coarser glinty microgeometry is something else I discussed. I'll kind of skim over this section because we're running a bit long and I want to spend some time on the last section. So we have this paper, which is very nice, basically stochastically generate these kind of microfacets that can yield glints, and you can control their density, and it's temporally coherent. And it introduces this very important concept of a multi-scale BRDF. Basically, technically, the original Nicodemus definition of a BRDF was like, it's this point sample, it's a single ray, it's all these infinitesimal things. And the multi-scale BRDF is like, no, I have an actual finite patch of area, I have actual finite cones, nothing is infinitesimal, and that's actually closer to the way people implement BRDFs in practice. And I think it's because of how closely BRDFs are tied to scale, I think this is, in a sense, a more fundamental concept than the sort of original definition of the BRDF. So the paper is worth reading for that alone, I think. And the technique in the previous paper is too slow, so here's one that does it in real time using various clever data structures. And here's one that's sort of specialized specifically to scratches. It's interesting because they actually do a multi-bounce physical ray simulation of what light does inside each scratch, and then they bake into this 2D table, and they can combine and you get this very nice looking rendering. Now, the bit I want to leave some time for is the other fundamental limitation of microfacet theory, which is wave optics. And I'm going to spend a little bit of time on the theory because some of the comments I made last year, some of them were either incomplete or incorrect. So I do want to correct the record. And this is going to be like the basics of wave optic scattering in a nutshell. So if you start a simple case, light's coming at normal incidence, so light's coming downwards, that's kind of the wavefront. And there are a few different domains of surface scale that have different effects on the light. But first, it's important to note, and this is one big misconception of mine that I've been able to correct since last year, not all scale is created equal. It really matters when you talk about how much scale matters for diffraction versus microfacet theory. There's a difference between height, basically displacement into the light direction, and displacement 90 degrees from the light direction. So when you talk about normal incidence, this is between the scale of the height and the scale of detail along the surface. And the height scale really is just a matter of degree. There's no such thing as, for bumps under this height, nothing happens or something else happens. It's just, if the higher the bumps, the stronger the effect. The lower the bumps, the weaker the effect. It's sort of this linear, or I don't know if it's really linear, but it's sort of this sliding scale. You don't have suddenly, when the bumps are bigger than this, then some completely different domain is entered. However, the sideways scale, that is like that. The sideways scale, you do have different domains with different effects. But in one respect, both these kinds of scale are the same. They both are relative to the light wavelength. None of this size stuff, the actual size in nanometers, whatever, doesn't matter. It matters only how many multiples of light wavelength you have. So is it 2 light wavelengths or a hundredth of a light wavelength? So the same surface will behave differently for ultraviolet light or for radio waves or for red light. Since I haven't been able to find out the proper terms for these, I'm just going to use the terms I made up. And I'm welcoming any correction if somebody manages to find the correct terms for these, because I haven't. So I'll start with nanogeometry, and that's a term I used last year to define geometry that causes diffraction. The relevant scale along the surface for nanogeometry is between about 1 wavelength and about 100 wavelengths. So any light in between that is going to cause diffraction. And if you have a very smooth surface that only has bumps, that rough, it will have a reflection that's this sort of perfect mirror reflection, this sort of delta function, perfectly coherent reflection. And diffraction, it kind of screws with it, but not in the way you would think. It doesn't spread it. It just borrows or steals some energy from it and spreads that. So now you have a mix. You have this perfect delta function spike of mirror reflection, and now you have this, the diffraction kind of steals half of it, let's say, and then spreads that out. And now you have the amount of light diffracted, like I said, depends on the height. So you have half as much height, half as much light will be diffracted, or maybe it's not linear, but it's some smooth relationship like that. Now the angle of the diffracted light depends on the sideways scale, right? The scale of roughness along the surface. And usually there's a mix of scales so that the light is spread in a continuous cone. Since these angles depend on the scale relative to the light wavelength, that means red light and green light and yellow light will all diffract at slightly different angles, and that's why diffraction has these kind of color shifts. A bit counterintuitively, the smaller detail, the wider the diffraction angle. The surface details that are 1 wavelength wide will diffract the light at 90 degrees. The ones that are like 100 wavelengths or more will diffract the light a tiny bit, maybe half a degree, and it starts merging into the mirror reflection. Basically, it starts not really being diffraction because it's too small. And that's why scales outside 1 wavelength to 100 wavelengths don't cause diffraction, kind of for opposite directions. Small If the bump is smaller than that, it diffracts it too much. It tries to diffract it more than 90 degrees, and that's impossible, so it doesn't get diffracted at all. And if a detail is much larger than 100 wavelengths, then it basically doesn't diffract it because it diffracts it by like a millionth of a degree, which is basically not diffracting it. And since wavelengths outside this range don't affect diffraction, you can think of diffraction as seeing the surface through this kind of band-limiting filter, right? That throws away all the spatial frequencies that are too large, like the big bump in the middle of the bottom. So the bottom surface is like the true surface, and the top surface is the surface for purposes of diffraction. So you have this big bump in the middle that's too big, so you filter that out, and you have all these small kind of jaggies, they're too small, that gets filtered out. And then for purposes of diffraction, if you're doing a diffraction calculation, you'll actually run this filter on the surface, and you'll see what the roughness is of that, and you'll use that in your calculations. Now, this was for normal incidence, but if light is coming from a different direction, then just remember that everything I said about height is just along the direction of the light, and everything I said about sideways is sideways relative to the light. But otherwise, it's the same picture pretty much, it just gets tilted. Now, the filter detail doesn't go away entirely. The stuff that's too big to be nanogeometry, it's too big to cause diffraction, that's the microgeometry we all know and love from microfacet theory. It tilts the surface, and it masks other parts of the surface, and does all that stuff. The detail that's too small to cause diffraction I'll call picogeometry. That is definitely not an official term in any way, but I haven't found a different one. And picogeometry actually does affect light in a different way, but we don't have time to talk about that today, hopefully in a future talk. And why do we care? I mean, for decades we didn't, pretty much. I mean, there was maybe a paper here or there. As I mentioned last year, some interesting work has shown that there's reason to believe that some of the visible shading we see from normal materials, from the Merrill database, from other materials, some of that is diffraction. Some of those long tails aren't NDF, they're diffraction. And this is a white paper. It's kind of breaking news. It's about to be published in the next few days. It's by Nicola Holshu and Romain Pakanowski, and Nicola and Romain were kind enough to give me kind of an early peek of it to help with this survey, since it seemed very relevant for the survey. And that's where I got the generalized Beckman NDF, but that's kind of a really small part of the paper. This white paper has a very interesting model. It combines a Cook-Torrance style microfacet model. You can see that that's the second column from the left, and that's the part that uses the generalized Beckman, with diffraction model. It's using the latest optical theory, the generalized Harvey-Shack theory, which dates from 2006, which may not sound very new, but most of the stuff in the literature doing wave stuff is like using Rayleigh-Rice and Beckman, Kirchhoff, and stuff that's like from the 60s and the 70s. So this is really brand new, and it is important. It's an important advance because all of those other theories, they had limitations. They can only do very smooth surfaces, or they can only do very rough surfaces, or they can only do small angles. And generalized Harvey-Shack is really the first theory that is considered general theory of scattering. And this paper combines it nicely with microfacet theory in a way that makes sense. Basically, they're saying that the diffraction BRDF is applied to each microfacet. So it's like your elemental microfacet BRDF. And then you have the kind of mirror part and you have the diffraction part. And it makes sense. It fits with that band limiting stuff I was talking about. So we're out of time. I won't be able to go into more detail, but the white paper itself should be up really soon. And if you're interested in stuff, it should be a good read. To wrap up, I'd like to thank some people who helped me with this talk, and thank you for listening.
I think we have time for one question. You can ask questions at the microphones in the center aisle. No? Well, let's thank our speaker again. Thanks very much, Natty. So our next speakers are Roger Cordes and Dan Lobel from ILM and Lucasfilm. So Roger is a digital production supervisor for Lucasfilm's Advanced Development Group. He oversees asset production, lighting, and overall look development effects for the group. And he's been with Lucasfilm organization since 2010, has focused primarily on real-time So time for a question or two. If someone would like to step up to one of the microphones. No one? Well, let's thank our speakers again.
Okay.
So our next speaker is Sebastian Heller. Sebastian is a rendering engineer within the Frostbite engine team at Electronic Arts. You can find him pushing visual quality and performance in many areas, such as physically based volumetric simulation and rendering, visual effects or post-processing, and many other areas. Before joining Frostbite, he worked at Dynamics YZ and Criterion Games. Thank you, Seb.
Thank you for the introduction. So yeah, I'm Seb, and today I'm going to present to you the physically based solution we use, we have developed in Frostbite to render the sky, atmosphere, and clouds. So just before I go further, I would like to thank all the people who helped in developing these techniques and proof it and iterate with us on it. So thanks BioWare, DICE, and Ghost. And also, of course, the rendering research community for all the useful results we can use in real time. So just a bit of context first. 2 years ago, we moved Frostbite to be based on a physically based framework when rendering surfaces. And this resulted in a really huge increase of visual quality. As you can see here, it's hard to tell which one is from the game and which one is from is a real photo, actually. But when it comes to sky and cloud and all that, the techniques we were using were still ad hoc. So for example, you could use HDRI capture for the sky, or gradient. For the atmosphere, you could use a regular depth and height fog and screen space light shaft. And for the cloud, you could use a high-quality panoramic texture or just planar cloud layers. And these techniques can be hard to make sure that all of them matches together, and to make sure also that you can blend them correctly if you want to do time of day, if you want to simulate time of day. So that was a lot of work for artists. And what we wanted to do is being able to render dynamic time of day with all the sky updating automatically when the sun is moving and the atmosphere, and also with weathering, also rendering clouds. And we wanted, of course, to be able to do that at 60 frames per second for some of our titles. And we wanted also that to be physically based, so that we wanted the material parameters to be decoupled from the lighting and make sure that we will have correct result first. And also have unified interaction. For example, the sun moving in the atmosphere should affect the cloud lighting and the global illumination, etc. So just some quick results. So you can see here Mirror's Edge Catalyst from DICE that's shipped this year. You can see dynamics sun moving and updating the sky, and also the global illumination automatically updating. And next is an early video from an unannounced BioWare title showing all the volumetric cloud, the time of day, all together with shadowing and all the lighting working together, basically. So very early results. So the outline of my presentation will be, first I will talk about how we render the sky and atmosphere, how we simulate them also. Then what we should consider when we render the sun. And then what do we do when we want to render clouds, also very volumetric clouds. So first, when we want to render sky and atmosphere, we need to understand what it is really. So we will consider atmosphere as a slab around the Earth. And one of the first components is standard air. So there is a definition of standard air. And when the light from the sun will interact with particles in the air, on Earth, it will happen what is called a Rayleigh scattering, And on Earth, the blue light will scatter more, and that's why you have blue light, blue sky at daytime. But when the sun is at the horizon, because the blue light will still scatter more the same way, only the red light will go further away, and that's why you have a red sunset, for instance. Another parameter, another type of scattering happening in the atmosphere is mist-scattering, which is due, in this case, more to larger particles in the atmosphere, such as pollutions or humidity, for instance. And one of the main characteristics of this scattering is that usually the light ray will not bounce uniformly when they bounce on the particles. So instead of that, they will bounce more forward along the light path, and that will result in some halo around the sun, which is visible usually. So what kind of technique can we use to render the sky? There's been multiple analytical models proposed, but usually these models have some simplified parameters and also are limited to ground views. There's been some spectral rendering solutions also which are more accurate, but in our case, for real time, we will stick to RGB. And one of the main work in that area is the one from Brunton, which is able, the model from Brunton is able to simulate multiple scattering, light shaft, and also all transmittance in the atmosphere and applied on the sun. And this is the model we wanted to be able to get in our case. But instead of, so Brunton is using lookup tables. Instead of using 4D lookup tables, for example, in our case, we are only going to use 3-dimension to simplify the problem. So these models are really well described, and the papers are, there's a lot of details in the papers, so I don't have the time to present them in details, but I can still show you quickly what are the lookup tables we are evaluating. So what are the inputs of these lookup tables? One is the relative height of the camera in the atmosphere. Another one is the sun zenith angle. And another one is the view zenith angle also. And from that, you can compute, for example, transmittance lookup table, which is the transmittance toward, from the point of view to the atmosphere boundary, or single scattering lookup table. And from that, you can iterate and compute a higher order scattering event, and just combine them all to get the final scattering lookup table that you will use to render the sky in atmosphere, for instance. So we can simulate the sky, but what are the coefficients one should use? So you have them here summarized, all of them. You can see the regular, Rayleigh, and mist scattering coefficients here. So you can see, for example, the blue is higher, which, as expected for Rayleigh. We have gathered them all from these papers, and the last one we have gathered from measured data, which is not common to see, but it has been. It is important to consider when rendering the sky, especially sunsets. I will show you a bit later. Why? So just to give you an idea of each of the atmosphere components, this is an atmosphere with a low density of particles, when showing Rayleigh scattering. This is with higher density, which corresponds to the regular Earth in our case. And this is with super dense atmosphere. Basically, you have a sunset in daytime. Oops. Oh, that's it. Yes, so when it comes to mist scattering, now you have that. This is without mist scattering. With mist scattering now, the default value to match Earth condition. And now is a super strong mist scattering. So you could say that in that case, it could be a sandstorm or something like that. And now absorption. So as I said, it has been reported as being very important to be able to recover the blueness of the sky at sunset, for instance. So this is the default thing you get if you do not use the ozone absorption. So the sky can look a bit gray, and maybe overall everything can look a bit yellow. But then you can, when you use absorption, you can recover the blueness of the sky, as you can see in real life. So artists can tweak the percentage of ozone if they want in the atmosphere, but we give them the value for the Earth we have recovered. So, okay, so now we have the lookup table. We want to render all our components. So first, you can just evaluate the single scattering lookup table at the maximum distance, and that will give you the sky. And then for the aerial perspective, which is the fog in the atmosphere, we do not just apply it like that on opaque. First, we render it into a camera-fitted volume. And for each depth slice, we just integrate the scattering and the transmittance. And then you can apply it on your scene. And so why do we do that? This is because it's very convenient to apply then after on all transparent to make sure that they fit in the scene and that there's no visual difference on transparent as compared to the other opaque objects. So this is a video showing that once you have the lookup table, you can just move the sun around and it will just automatically update. Everything should fit. No. Some out of order animation. So basically the sky will, and aerial perspective, yes, will update, but you still have to update some other components like your sky environment map, your local reflection volumes, and you also update your global illumination system if you have one, to make sure that everything should fit, otherwise it's going to be very visible, especially at sunset. So when it comes to performance now, the lookup table updates are very, very expensive, so you need to be careful with that, especially if you update, for example, the atmosphere properties, because that will trigger an update of the lookup table. That's the only case where you need to do it. And to not have to pay a high cost, we just distribute it over multiple frames. You can see, for example, if you accept latency of 19 frames, then the cost come down from 3.5 milliseconds to 0.2 milliseconds. And here on Xbox One, just to give you an idea, the cost of rendering the sky is 0.5 milliseconds roughly. Okay, so we're done with the sky and atmosphere rendering part. Let's see what we need to consider when it comes to rendering the sun. So in Frostbite, artists specify illuminance at the ground level for the sun at zenith. We do that because that's easier for them to understand what's going to happen, and it's more predictable. And from that, then if we want to render the sun disk, we need to recover the luminance, because that's what we store in our buffer. So we just invert the transmittance in the atmosphere, and also take into account the sun solid angle that artists can set up. And from that, we just recover the outer space luminance. And if we want to have correct lighting for the current sun position after that, when the sun is moving in the atmosphere during the game, we just need to reapply all that, doing the inverse, basically. And from that, we can recover the illuminance at ground level. So as I said, we have recovered the outer space luminance for the sun, so we can render the sun disk. But by default, it looks a bit off. If you want to fix that, you need to apply the transmittance lookup table per pixel. And that will give you a sun that matches what you would expect in these conditions. Okay, so we have sky, atmosphere, sun. Let's talk about cloud rendering. So there's been multiple models that have been proposed to render clouds. One of the best one, in my opinion, is the one from Booters, which uses a combination of meshes, hypertextures, and rematching to achieve really high quality results with multi-scattering. But this is still expensive today to render. Youssef also proposed a nice splatting-based approach of particle splatting-based with also pre-integrated multi-scattering per particle. But the visuals were not matching what we wanted to do. That was not matching our target. But last year, Schneider proposed a very nice technique which can render different types of cloud, different shapes under dynamic weather, dynamic shadowing, dynamic lighting, and this is the type of solution that we wanted to pursue, actually. So I'm not going to go into the details of Schneider because there's a lot of stuff, and the presentation from last year is awesome, so you should check it out if you still have not. But I will just talk about some improvements we are doing using energy conservative scattering formulation, or why should we use a two-lobe phase function at least, and a bit more interaction. So what we need to do to render volumetric cloud, basically. For that, we use rematching, the same as Schneider. And when you do rematching, you can integrate transmittance, which is the result of the extinction coefficient from the participating media. And you can see here that will be the occlusion from the cloud on the background. Then you need to lit your cloud. So for each sample, you also need to evaluate the ambient lighting. In our case, this will come from a pre-filtered sky environment map. And also, you need to, of course, take into account the sun. But if you just take into account sun scattering doesn't look interesting. You also need to remarch the self-shadowing of the cloud in order to get all these nice details on the cloud. And last but not the least, it's the phase function, which, because when light is bouncing on particles in a cloud, it does not bounce uniformly. It will follow a specific pattern. I will show you a bit more later why. But this is important to have like the silver lining effect that really defines cloud look. And here's just a picture to show you like a real-life reference. So we are lacking like very, very, very fine-grained details and multi-scattering, but basically we have the main component. So first, how do you integrate scattering when you rematch your volumetric data? Usually it's done with this sort of function, where you first update scattering and then update your transmittance. But there is a problem, because to update your scattering, you need transmittance, and then you need to update your transmittance, so you don't know which one you should do first or the other. And this is a bit wrong, in fact. So what we propose to use is an energy conservative integration function of the scattering. I won't give you details, but there's a shadow talk demo you can refer offline. So this is the first version where you update scattering first and then transmittance. But you can see that now ambient is super bright, and this is because this cloud here in the specific shot are very dense, so the scattering value is super high, and we're also doing very large step in the atmosphere. And this is now when you update the result when you update transmittance first and then scattering. So in this case, the cloud will look super dark, and also you will miss some of the silver lining effect, and the cloud looks even like dirt, so it's not interesting. And this is the result when you use the energy conservative formulation. Everything looks more balanced, as more as what you would expect. I can show you more why this is interesting also. So in the top left, you have the wrong integration with only 21 samples. And if you do more samples, then it starts to converge to something that is more expected. But of course, that's going to be expensive. But with the improved scattering, you can just use 21 samples, and you have already converged to a good solution. So phase function, the cloud phase function is super complex. You can see one example here in blue, the top right, which comes from Butos. And you can see some very complex shape, like very strong forward spike, and also like very complex tail, which results, for example, in a glowy halo or pseudo-specular you can see sometimes when you fly. And this is backward scattering is super important, because if you only try to approximate this blue phase function with the green usual Henning-Greenstein phase function, you will miss that tail, which is backward scattering. And this is important, I will show you after. So instead, what we'll propose this has been proposed before already, is to use a two-lobe phase function. And we tried first to make a best fit onto the complex cloud shape, cloud phase function. But this was not really working, and we think this is because we do not have multiple scattering simulation. Like the back scattering in that case was not very visible still. So what we do, in fact, we just give artists the control over all the parameters for that function. And it makes sense, because like the blue function you can see here, the cloud phase function, this is just one example for one distribution of particles and one distribution of radius for these particles. So in the end, it can be more complex and different, so we prefer give the control to the artist in that case. So this is just some cloud rendered with only forward. You can see the lobe, the phase function at the top left with only forward scattering. And this is the same cloud with forward and backward scattering. So you can see that the scattering, the silver lining shape is a bit less intense, and that is expected in an energy conservative solution. But when you look away from the sun, if you only have forward scattering, then the cloud will look will only have ambient color and lighting on them, and this is making them look flat and uninteresting. But if you then use the dual lobe phase function, then you get more details out of them, and you also see some self-shadowing effect. So more details, self-shadowing effect. So this definitely makes them look more like what you would expect in real life. okay, so now we can render all the clouds we need. But if you still render them just like that, you will have a visual mismatch because you need to take into account the different weather conditions that can happen when artists will increase the density. But you can have a visual mismatch then. You also need to apply the aerial perspective to them. So one could just evaluate the aerial perspective per sample and while you remarch, but that can be expensive. So what we do instead is we just evaluate the mean depth of the cloud weighted by transmittance, and that will basically tell us which sample we should use to evaluate the aerial perspective to apply on the cloud as a post on top. And that is just, and basically that formulation of weighted transmittance will just keep this position in front of the cloud interface. And this is the result now. So now there's no visual artifact, it matches. But when the clouds are becoming so dense like that, you will expect that it will be less intense. So something is missing. So what one could do is just remarch in the atmosphere and get like volumetric light shadow, volumetric shadow in the atmosphere and occlude the aerial perspective. But that is a bit expensive, so we wanted a cheaper solution first. And for that, we are just going to sample at ground level the cloud layer. And first we sample transmittance, and that will be used to occlude the scattering in the aerial perspective fitted camera texture. And we also sample the cloud luminance, which is used and reinjected into the aerial perspective to make sure we have a matching color in the aerial perspective that matches basically the cloud of the color of the cloud, and all as a function of their parameters and all that, everything will still stay coherent. And so we use that local effect to the camera as a global effect in that case. That's what we have today. And you can see the final result here. So the cloud become more dense, basically hiding all the lighting from the sun and the sky. And you can see more like a blue color than now coming from the sky, from the cloud. And this can look, for example, this is an example of real-life photography of the same case, roughly. So just to give you an idea, some performance numbers. So in our case, what we do, for example, for the main view, we just use half resolution. We also do temporal reprojection as Schneider, but that's it basically. So just a final video showing the final result of everything integrated, to the cloud moving, the sky, like changing from nighttime to daytime. You can see there was the moon here with rendered with our celestial system. We can also run the stars, and then you end up having daytime. And also here, this is the. You can see this. This is we tried to eyeball the Mars atmosphere basically. I can restart that. Doesn't restart? Right. Yes, so you can see at the beginning the Mars reddish color, and then the blue sunset that's characteristic from Mars. So it's just eyeball because we have not found Mars atmosphere scattering properties. That would be useful maybe. So yeah, just to conclude, so I just presented you the physically based framework we're using to render sky, atmosphere, and cloud in Frostbite. And we use also to be able to render all these participating media elements with an energy conservative formulation for the scattering. And I showed you that this can support dynamic time of day, dynamic weather also. We try to use the same definition as Schneider for the cloud weather, how it can evolve. And yes, and there's also a lot of different, I just showed also that it's important to have all different components interacting together. So the sky lighting should affect global illumination, and for example, the cloud coverage should affect also the aerial perspective. All that should match to be visually coherent. Then, by default, in Frostbite, the artists will use will get, when they use that system the first time, they will get the Earth, Sun, and Moon physical values, and then it can be changed. All the parameters, the physically based participating media parameters can be changed to match any extraterrestrial world they would like to. And And if you want more details about the cloud, the sky rendering, for example, you can refer to that presentation, Mirror's presentation by Fabien Christin this year. So this is used in production, and the next game getting out is FIFA and Mass Effect Andromeda, using the sky system especially. I don't know if I have time for... So yeah, of course, what do we want to do in the future? So there's lots of things to do. For example, the aerial perspective being affected by the cloud cover and all that, we would like to use proper remarching into the atmosphere with proper, to get proper volumetric light shaft automatically. You could also pre-integrate the sky according to the current phase function in order to get better ambient into the clouds. Yeah, the not dynamic weather right now that we use, same as Schneider, we would like to make that even more dynamic. This is a bit simple today. And there's still a huge research area of research, which is how do we really update efficiently all the reflection volumes we have in the world. Okay, just a bunch of references. And yeah, we are hiring, so if you're interested, don't hesitate to get in touch. Okay, thank you.
I think we have time for a question. If anyone would like to step up from to one of the microphones.
There will be additional notes also coming later. Still working on it.
Hello.
Hello.
Thank you for the presentation. I had a question about shadows. Do you do standard shadow maps or retrace shadows from the ground to the sun?
Oh, on the ground, you mean?
Yes.
Yes, so we just bake the cloud. They are also baked into a texture that's projected on the ground. It's 2D. It doesn't take into account the terrain shape, for example. We just bake it and blur it a little bit to make it softer. And this moves all along with the cloud motion, also with the wind.
Okay, but how do you take into account the direction of the sun in this case? You bake them only like when the sun is on the top of the cloud layer, and then you just...
It takes into account the sun direction, yeah.
So you bake like several of them? Or you just bake one texture, or you update it when the sun moves?
I'm not sure I understand all the question then.
Well,
it's all dynamically updated from the cloud state. So yeah, it will. If you make the cloud denser, then the shadow will become also like everything will look darker.
Okay. Okay.
Or we can talk after if it was not clear. Sorry.
Thank you.
Let's thank our speaker again.
Thank you.
So that's the end of the first half, and we'll be back again promptly at 3:45. I'll do that and start the next. Yeah, that's not bad. Again in 1 minute. So hello everyone, welcome back. I'll remind you again of the course webpage. We actually have some slides already online there now, so you can go online and check them out if you're interested. It's my pleasure to welcome the first speaker of the second half of the course, Sébastien Lagarde. Seb is a software engineering graduate who's worked in the game industry since 2003. He's an engine programmer with an expertise in rendering. He's worked on many consoles, on many titles, from small casual games to AAA. He's worked at Dontnod, EA Frostbite, and now he's at Unity Technologies as the Director of Rendering Research. Over to you, Seb.
Hello. So I'm Sébastien Lagarde, and with my two artist co-workers, Sébastien Lachambre and Cyril Jovert, we have tried to set up an easy method to capture accurate panoramic high dimension images. This talk is oriented toward artists. We want to use HDRI as a light source to easily reproduce lighting from the real world and to better integrate a CG object inside an environment. This is a process that is widely used today. Such HDRI needs to be accurate. It means that it must capture the full range of lighting in the scene without clipping. It must have minimal lens artifacts, and it must be linear, and it shouldn't include any artistic effects. When talking about full range HDRI, we mean this. So left is unclamped HDRI, and right is a clamped one. When changing the exposure, we can see that the sun disk is slightly less intense on the clamped one. But this small difference has a huge impact on the lighting. This picture shows the equipment and software that we use at Unity. We have tried to make our equipment setup affordable and have avoided using any custom devices to ensure our result can be reproduced. We use a Canon 6D with a Sigma fisheye lens, a Manfrotto tripod with a Nodal Ninja head. We also try to stick to a small number of software tools and favor artist-friendly ones, such as Photoshop or PTGui. We use a heavy tripod in order to do stable capture in outdoor environments, since wind can be a problem, particularly with long exposure time. The Nodal Ninja head is used to align the lens center to a pivot point, and the camera must be perfectly parallel to the ground plane. Don't hesitate to spend time on alignment, as it vastly reduces the time spent on stitching later. We use a remote controller named Camera Ranger to record the sequence of shots that we want to do. It allows us to reduce shaking during acquisition. To build a 360 panorama, we use a fisheye lens. It provides 180-degree field of view. We have divided the 360 panorama in 6 views. There is 3 views towards the sky and 3 views towards the ground. And there is several optical artifacts in the lens that appear with distance from the lens center. That's why we have chosen a 30-degree elevation instead of 45 degrees. The goal is to get more accuracy at the horizon. This is where there is often a lot of moving elements, like pedestrians, that we need to remove. To remove the tripod, we capture an extra bottom view. We place a marker on the ground under the tripod at the pivot point and move the tripod, then rotate the camera with the help of the nadir editor. So of course, we shot with a manual mode on a raw format, and we disable automatic white balancing and color contrast enhancing features. An HDRI is a combination of shots of varying exposures. The exposure is based on 3 parameters: aperture, ISO, and shutter speed. And a given combination of these 3 parameters can be summarized by an exposure value, or EV. Unity HDRI are acquired with fixed ISO and aperture values, and we only vary the shutter speed to control the exposure. We set the ISO to 100 to minimize the noise. And for the aperture, we want accurate images for both near and far scene. Small aperture cause diffraction, produce softer result and significant flares. And wide aperture have significant vignetting, low depth of field and aberration are more prevalent. So the best aperture should provide sharp images. On our test, we found that f8 provides the sharpest image, while at the same time minimizing lens artifacts. For the shutter speed, the value will depend on the scene range. Shutter speed controls the amount of time that the sensor is exposed to light. With camera on the tripod, we locate the darkest and brightest areas of the panorama. Then we tweak the shutter speed until the histogram of the camera preview is not clipped. To simplify the process, we restrict ourselves to power of 2 shutter speed. And to get the scene EV range and the number of shots to perform, we use the property that doubling the shutter speed is an increment of 1 EV. We use this table here to help us. With the shutter speed for bright and dark areas, we calculate the EV range. So in this example, it's 6. And with an EV step of 1, it means that we will require 7 shots with a shutter speed shown in this table. And this shot sequence is programmed in CamRanger. So this is an example of all the shots to take with the previous example and an EV step of 3. As we vary only the shutter speed, we are limited by the minimum shutter speed of camera. It's 1 divided by 4,000 seconds for a Canon 6D. And seen with very bright light source, like the sun or spotlight in a football stadium, can emit up to 30 EV, and this will be clipped. To deal with very bright light sources, we use neutral density filters, or ND filters. ND filters can reduce the amount of light entering the lens. ND filter strength is expressed by a number that is the power of 2 of the EV reduction it provides. ND filters can be changed, and their EV reduction is added in this case. Again, we restrict ourselves to power of 2 ND filters to simplify our process. For scene with very bright light sources, the first step is to determine the ND filters to use. For the 0-degree view of our process, we turn the camera to face the light source. We set up the shutter speed to the minimum allowed. Then we install 1 or more ND filters in front of the lens until the light disappears on the preview. Once we know the ND filters to use, we increase the shutter speed until the light source is not clipped, like before. To get the EV range and the shutter speed for the shot, we use these big tables. So it lists the power of 2 ND filters that we use at Unity. ND filters allow us to emulate a decrease of EV without changing the camera settings. You can think of it as if you were able to decrease the shutter speed below the camera's limit. It's like a virtual shutter speed value. So let's say our light source disappears with a ND 500. And we find the bright area shutter speed to be 1 divided by 1,000. And we get a list of shutter speed values. We do not take into account the EV0 as it is redundant. And here I just change the green vertical section to horizontal. And I concatenate with our regular shutter speed table. With an EV step of 1, the green table gives the number of shots to do with the ND filters and with which shutter speed values. After the ND filter shots, we perform a second round of shots, but without the ND filters. This enable range, in this case, is just the number of shots -1. So this is an example of shots that have been captured for a scene with a 23 EV. In practice, the sun in a clear sky always requires ND 1000 plus ND 500 filters. Human vision does chrominance adaptation to always perceive a white object as white, whatever the lighting condition. And in photography, we try to obtain an image that is close to a human vision. We simulate this adaptation with a process called white balancing. Performing uniform white balancing on 360 view of a panorama is incorrect, and because human eyes have a smaller field of view. And eyes can perceive different lighting conditions depending on the orientation in the CG scene, so best is to do the white balancing at visualization time. We choose to stay with classic white balancing for now, and we capture an additional bottom view with a color checker to do it later. In addition to white balance, we also want to perform luminance calibration. With our workflow, the HDRI produces as relative luminance, and we want to convert it to absolute luminance that matches the real world. This calibration requires taking light measurement during the capture. There is cheap device or expensive device to do this, so lux meter, spot meter, or luminance meter. And we choose to use the lux meter for this step, as it is cheap and accessible. It captures the light coming from the upper hemisphere of the meter, and we do the measurement of the illuminance of the scene at the camera pivot point. We use D0 to convert our raw file to TIFF. It allows us to not perform the white balancing store in the metadata. And D0 has also a good linear reconstruction that is important to have a correct HDR value. D0 seems to be the only software that conserves linearity. Other softwares such as Adobe Camera Raw apply some gamma conversion on artistic suite. Camera optics system cause a lot of artifacts, and we try to fix what we can. For veiling glare and lens flare, we choose to not correct them. And chromatic aberration is caused by the variation in refractive index for different light wavelengths of the lens. And to correct lateral chromatic aberration, we use the Photoshop lens correction tool. To correct the actual chromatic aberration, we use a software from Nikon called View NX2. And for vignetting can be significant. It depends on the lens and the aperture. And we have developed a simple method to characterize the lens vignetting. We take a direct shot of a piece of paper on front of a widescreen. And shooting the screen directly exhibits the pattern of LED, so we avoid it. And the paper also has a pattern, so when we take the shot, we move it quickly to blur it a bit. Then in Photoshop, we blur and normalize the image. We use the same setup to characterize our ND filters. To recover the vignetting, we divide the picture taken with the ND filters by one taken without the ND filters. The ND filters is not always homogeneous and has a very slight chromatic shift. We can see it on the image here in yellow. The image shows the vignetting characterization of our various Oya ND filters. It means that there is a very slight blue tint, and the image has been rescaled so you can see it. The full characterization is lens vignetting multiplied by each ND filter's vignetting. And to apply vignetting correction, we divide vignetted shot by the full characterization in Photoshop. With our equipment on our 120-degree FOV shots, we found that correction was not necessary. In addition to characterize vignetting, our setup allows us to detect when an ND filter doesn't match its specification with the compensation to apply. Our ND 1000 is not a through 10 EV reduction, and when we use it, we correct our shots. We use P-degree to create our HDR panorama. We correct the distortion inside P-degree, stitch our shots, and generate two HDR, one with and one without color checker. PTGUI apply a gamma correction on the 16 TIFF images, so we need to convert our TIFF from 16 to 32. If the equipment is perfectly aligned, then the teaching should be easy. To build the HDR, PTGUI uses exposure embedded in EXIF, and this information is not changed when using ND filters, and so it produces wrong result. We must edit exposure manually in PTGUI with the value of the virtual shutter speed I mentioned earlier in our table. This is an example of an outputted HDRI. You can see the various exposure with the intense sun disk. For white balance, we have developed a Photoshop suite. We white balance the color checker contained in the HDRI with the color checker and applies again to the other HDRI. For luminance calibration, we need to find the ratio between the real-world illuminance that we get with the luxmeter and the illuminance from the HDR panorama. The math to get the illuminance is not really artist-friendly, but we have found a way to do this integral with the Photoshop script. The script will apply the ratio of light measurement to the white balance HDRI. There is the full detail of this in the course note. So at Unity, we use HDRI for our new LookDev development tool. It allows us to visualize an asset under various lighting conditions represented by an HDRI. As the lighting is perfect, the artist can validate their materials. We have an HDRI buzzer in these tools and an option to generate earth shadow for one very bright light source. Absolute HDRI, in the case, the game engine uses physically based light unit for other lights. This ensures that values are in the right range. And Unity doesn't support this yet, but we have planned for it. To conclude, we think our process to capture accurate HDRI is a good balance between time, price, quality, and complexity. Our artists are able to shoot HDRI in 10 minutes today. We have tried to limit the number of software packages and avoid custom devices to remove lens artifacts. Lens artifacts are very difficult to correct, and we don't think we can improve it and stay artist-friendly. There is plenty of detail about our process, which we elaborate in our course note. Thank you.
We have time for a question or two if people would like to go to the microphones. No one? Well, let's thank Seb again. So our next speaker is Brian Karras. Brian is a senior graphics programmer at Epic Games, where he works on Unreal Engine 4, focusing on physically based shading, anti-aliasing, and geometry. And prior to joining Epic in 2012, he was employed at Human Head Studios and created the renderer for Prey 2.
Thanks. I'm Brian Karras. I'm from Epic Games. I'm going to be talking about physically based hair shading in Unreal. The motivation behind this work was to create a physically based shading model for hair that would be usable for games. There's been a ton of great advancements in hair rendering recently, but not really in the shading realm. It is common to hear every material in our game is PBR except hair. Most everyone in games is still using the Kajia K shading model. So let's change that. Before we start any work like this, we like to get a ton of photo reference so that we can compare our results to vet any of our assumptions and final art, as well as the algorithm as it's in development. and what we finally get to. So this was some simple curl reference to get a bunch of different color samples from hair. These are human hair hair extensions that we purchased. In addition, we also had a professional stylist come into the studio and style some people's hair to look like those of characters that we would have in Paragon. In this case, this is a 3-point lighting setup for the character Twin Blast. Here is ambient light reference. And this is a single light for the character Sparrow, seeing what the lighting looks like from a number of different directions. Our hair shading model is based on the kind of framework that was developed by Marshner. Marshner made a breakdown of the light paths for hair fibers. The model is modeling the shading for a single hair fiber. The paths are named by the R for reflection and T for transmission events as that individual paths of light encounter. So the R path is highlighted in red here. This is the light ray that reflects off the front of a hair fiber. The TT path, this is the light ray that transmits through the front of the fiber, passes through the interior, which has a color due to it, and it colors the light due to absorption, and then it transmits through out the other side. And finally, the TRT path. This is a light ray that transmits through the front of the fiber, passes through the colored interior, reflects off the opposite side, passes through that interior again, and then transmits out the front. We can keep on going with these sort of internal bounces off to infinity, but those are typically much dimmer to the point of being negligible because of the amount of times that absorption has been having for the light ray. To see what these look like in the real world setting, here we've got an image that shows both the R and TT highlights from the light paths. The R path is the white highlight that you see here, and this is white due to not passing through the interior of the fiber at all. The TRT path is colored due to passing through the fiber twice. They're separated from one another due to the tilted cuticle scales that are on the fiber. Going back to this image here, you can see that human hair fibers aren't perfect cylinders. They have these cuticles on them that end up making the geometry more like a stack of cups than a perfect cylinder. That will end up causing these two highlights to separate from one another. The TT path can be seen from the other side. This is colored since the light is passing through the interior of the fiber, but since it only passes through once, it will be less saturated than the TRT path. Marshner's factorization of the shading separates things into a sum of these lobes, P standing for the number of times that the path passes through the interior. So it goes from R, TT, TRT, and so on. And all of these individual lobes get summed up. Each lobe is also broken into two separate functions to better simplify the math for this. These are the longitudinal and azimuthal scattering functions M and N. The longitudinal function describes the scattering down the length of the fiber, where the azimuthal function describes it radially around the fiber. You can see that from the left and right side diagram as far as what these two components are trying to describe. At this point, real-time Marshner has been done before. It has been made performant through the use of lookup tables. This requires baking all of the parameters that wouldn't be the dimensions of the lookup table into that lookup table, though. So if we go back to these two functions, those being the inputs, you've got a 2-dimensional and a 3-dimensional lookup table. but all of the other parameters that describe the hair wouldn't be represented there unless you increase the dimensionality by a huge amount. Baking in all of those parameters into a single lookup table for a certain particular type of hair just isn't practical for us, because we need to represent many different colors of hair with different roughness, and in some cases those need to vary within the very same hairstyle. So we can have characters with streaks of color in their hair or patterns in fur. Here's just some examples, but we have many more characters coming for Paragon that haven't even been announced yet that I can't show you, but trust me in that we basically have to represent everything under the sun as in regards to hair. So our shading model, we started with the latest research from Weta as far as what they're using for hair shading, and made an approximation of it. We started by creating our reference implementation within Unreal Engine, and then started working down and approximating component by component. That model can model all of the infinite length paths, but we only approximate the RRTT and TRT paths that I showed before. We don't handle eccentricity of the hair fibers. Most of this work involves just a lot of curve fitting and function approximation. There's a lot of theory that I don't have time right now to go through where all of the basis of this prior work came from, but I will refer you to the original papers for this. And if you don't notice, there's references down at the bottom of these slides for all the different places that you can look. So let's start diving into these functions. First with the longitudinal scattering function. One of the improvements that Weta's model made over Marshner's original one is that there is an energy conserving longitudinal scattering function. Unfortunately, this is a bit too expensive for our purposes, especially there's a bezel function in there, the I0 that is just too heavyweight. Even the approximation of it is just too heavyweight for us to do for real-time purposes. We ended up using the Gaussian instead, which isn't properly energy conserving. This is an area in particular I'd like to improve. I believe we could probably come up with an approximated model that's still properly energy conserving, but that's what we use. We did end up using what is azimuthal dependent modification from their follow-up paper. For the R path, at least, this is cheap enough and looks slightly better. For other paths, it's too complex and does not have big enough impact to warrant its use. The azimuthal function for R is fairly simple. The distribution function is just cosine half phi. Using a trig identity, we can skip any inverse trig functions. The attenuation is just the Fresnel function with the input shown here. We can see comparing the reference implementation to our approximation. Here's the reference for just the R component. And here is our approximation. Which looks close. There's some bit difference in the sharpness of some of the highlights that would be improved if we use the energy conserving function. For the azimuthal function, azimuthal functions for the other paths, Weta solved the paths internal to the fiber through numerical integration with a Gaussian detector. This is a very nice generalization of the problem, but is far too expensive for us, for our purposes. It isn't really important to understand the integral for the sake of understanding our approximation here. Basically just know that it's too expensive to solve as is. Instead, we're going to solve the other paths as single lobes, more in line with how Marshner originally did. It is useful to understand the attenuation term A here. This is broken into two subterms, the Fresnel and absorption function, which is listed there. For TT, the exact solution for the offset H, which is used in some of those functions on the previous slide, is this. We've got a, we need H, which is the offset from the center of the fiber of the light path, and an eta prime is the modified index of refraction. For this function for H, we can simplify it a bit here using some trig identities and moving some stuff around, but it's heavier than I'd like. So on to approximation. They start by graphing the function, seeing what it looks like. Function approximation like this is somewhat of a black art, but the way I go about it is make some intelligent guesses about what can be removed or replaced. Try and see what works, and this is what I came up with. So this uses a cosine half phi that we had calculated previously, which means we don't have to do any inverse trig to find phi. If we ignore the sine of h, which you can see later turns out to not be relevant for our use, we have this function which is cheaper and looks close enough for our purposes. We also need to calculate the modified index of refraction. So the original equation for calculating is that, and we start with the original index of refraction of 1.55 for human hair. Plugging that in and approximating, we get this below function, which is cheaper to calculate and has a really low error. There are more details in the slide notes, so release later, of how we came up with some of these approximations. The absorption term is this function here that was in Wetta's paper. We chose to use Pixar's absorption term instead because we found the look to be a bit more pleasant, especially for the TT term. C in this equation is the base color of hair. When we plug in this formula for the gamma t and simplify the function, it turns into this, assuming that we have picked a function for C that makes color picking for the artist fairly intuitive. For the distribution, for the azimuthal TT, we started with Pixar's logistic distribution function approximation. They had a very nice approximation that involved a formula for S that was fitting this logistic function. That formula for S was a bit too heavyweight for us, so I replaced it with the constant 0.35. The graph there of the function fit to that, which we again replaced the logistic function with a Gaussian that makes it even faster than doing the logistic even with a constant. So we look at, here is the reference for the TT component, and here is our approximation, which ends up looking pretty close even though we've taken some liberties. For the TRT component, we have to be pretty brutal. Marshner solved this and the glints with a root finding for H, which has multiple solutions, which means multiple lobes. Wetta solved it with heavy numerical integration. Pixar solved it with very large lookup tables. I chose to use a single lobe H for the offset of the path from the fiber center. For the purposes of Fresnel at least, I used this constant. For the absorption term, all use of H or the modified index of refraction are gone, again replaced by a constant. The distribution, I again started with the logistic function and chose the constant for S of 0.15. And then again fit that with a Gaussian to replace the logistic. The graph shows the difference between that logistic function and the Gaussian. Here showing the reference for the TRT component and this approximation, even though we've been very liberal in replacing some very complex terms. It's not terribly far off from the goal. So adding up all these components together, here is the reference of R plus TT plus TRT, and here's what our approximation looks like. But it's still missing something because this doesn't look like very realistic hair. We are missing scattering. We need to render a volume of hair, not just a single strand like the models describe. This means multiple scattering events of a light path as it goes through the volume. A light will bounce from one hair to the next, transmit through multiple hairs. This is very important for the look of hair, particularly for light hair color, because their light will be far less absorbed and can end up taking a longer path through the hair volume before it gets dim enough to not be able to see anymore. Path tracing is certainly not practical for us in real time. We investigated making a simplification of dual scattering. This definitely deserves some further research. We ran out of time making a path traced reference to compare against. It feels kind of wrong to present this part in a physically based shading course, because basically this next part is just an ad hoc model. But let's turn this instead to a call of arms to have someone else make a better approximation than what I have here. This is definitely the biggest improvement that could be made, is to replace this term. So we used ideas from Agni's philosophy demo. We don't author a normal, instead use a fake normal instead. It's theoretically better to have an actual normal either authored, whether it be calculated by tracing similar to bent normals, or derived from a filtered distance field of the volume. But in my tests, I found little extra benefit from an authored normal when filtered shadowing was applied. Wait, oops, skip forward too much. Making authored normals ends up saving both artist time and precious G-buffer space. Very quick run through of what the scattering equation is doing. We've got the C, which is the base color. There is a wrapped Lambert term in there, and then there is an absorption, which is just the color getting more saturated with the path of the light. In this case, we use the amount of shadow. Our shadow maps are sampled with an exponential fall off because of the amount that's getting absorbed as the light path goes through the volume. That path length will end up getting derived from that shadow value. So this is a look at what our scattering approximation looks like. For this case, I don't have the reference to compare it against. It's just this. So here is the complete model now with scattering combined in. And here is the complete approximation. Here are the artist parameters that we end up tuning the values within these formulas. Running a little low on time here, so I'll skip forward some. Mentioned already that rely on shadows for the shading model. It's absolutely vital for the look, which is easy to see by disabling them. The shadow maps are PCF filtered with an exponential fall off, which looks pretty convincing, but what about for non-shadowing lights, whether these be from effects or low-end hardware, or whatever reasons why we might need to disable shadow maps. Found that a screen space raycast against the depth buffer of the screen was a very good solution of this for hair. For environment lighting, we researched a number of different approaches. The most intriguing approximates a Marshner model with the circular Gaussians, which can be analytically integrated against spherical Gaussian lights. Since this is basically what we have for both the longitudinal and azimuthal functions, this could fit well with the rest of our approach. But in the end, it wasn't worth the development time to be that sophisticated. So we make a single lookup of the environment lighting in the fake normal direction and sampled our spherical harmonic with that, which is essentially the environment convolved. and use that as a single directional light source, and then make some minor modifications to the shading model to make this end up looking somewhat convincing. We had to make those modifications because we don't have a shadowing term, so we don't want to end up in that glowing head case that we had in the prior slides. So here's a comparison of here's what the reference looks like, here's our approximation, and a few other similar comparisons in different lighting environments. I'll leave you with some shots of this human head that we'll be releasing in the next version of Unreal. So there'll be a high quality example asset to look at how to author similar things than what we're doing in Paragon. And lastly, thanks to Epic, our character art team that made all of this, these characters, and to Stephen Hill and Stevie McCulley for reviewing these slides. Thanks.
Does anyone have any questions? No? Okay, thanks, Brian, again. So our next speaker is Jorge Jimenez. Jorge is a graphics R&D technical director at Activision Blizzard. He received his PhD in real-time graphics from University of Zaragoza in Spain in 2012. And he's made contributions to conferences, books, and journals, including SIGGRAPH and GDC, the GPU Pro Series, Game Developer Magazine, and ACM Transactions on graphics. At Activision, he's currently working on the Call of Duty franchise, including Advanced Warfare and Black Ops 3. And his interests include photorealism, special effects, and attention to the details.
Hi, thank you for the introduction. So I will be talking